I'm excited to present our work on DynamIPs, where we analyze address assignment practices in IPv4 and IPv6. This was work done at CAIDA with Alberto and with Stephen from the RIPE NCC and John and Philip from Akamai. Let me begin with the motivation. Can IP addresses be used to identify residential subscribers? Probably yes, if the address is assigned statically, but how about dynamic addresses that are typically assigned in residential networks? In this work, we investigate address assignment dynamics of residential subscribers, focusing on IPv6. While prior work has investigated dynamics in IPv4 to some extent, there is little work that investigates address assignment in IPv6. In contrast to the address space scarcity in v4, which often forces ISPs to reclaim addresses aggressively, the 128-bit address space of IPv6 means that there is no danger of running out of addresses anytime soon. This massive address space also offers enormous flexibility, allowing ISPs to rotate the assigned addresses quickly if they so desire. So we empirically examine the temporal dynamics in IPv6 and analyze how long v6 addresses are assigned to residential subscribers. We also examine spatial dynamics. Where do addresses move upon reassignment, and what is the length of IPv6 prefixes that is assigned to residential subscribers? Now, why do we care? Because several applications expect that addresses can be subscriber identifiers and would benefit from an empirical assessment of this expectation. Host reputation services seek to blacklist or rate limit packets from malicious IP addresses. However, it's important to allow other subscribers to continue access, so it's vital to keep reputation services up to date. IP geolocation services seek to identify where various subscribers are located based on their address, and there are myriad applications of geolocation. Active probing techniques seek to identify target IP addresses that they can probe over time to measure various phenomena, including vulnerabilities and internet outages, and also to measure internet topology. But other than these applications, there are also larger privacy issues at stake here. If IP addresses can be used as long-term subscriber identifiers, there are serious privacy implications since subscribers can be tracked long-term. In order to understand if addresses can indeed be used as identifiers, let's dig into a little bit of background first. Most of you are likely familiar with the typical IPv4 residential setting. When a home router boots up, it requests an address from the ISP's DHCP or radius server. The server has a pool of addresses out of which it assigns addresses to its customers. Addresses in the same pool typically share geographic and network topology. It chooses one of these addresses and assigns it to the home router. When user devices communicate to the internet, the publicly visible address is that of the home router. Let us now contrast this scenario with IPv6. Similar to v4, the home router requests addresses from the ISP when it boots up. However, instead of assigning a single IP address as done in v4, the server now assigns an entire prefix. In this example, the server has assigned a /64 prefix to the home router. Devices in the home now use this /64 prefix to obtain the 64-bit network part of their addresses. They generate the 64-bit host part component of their IPv6 addresses autonomously. Most laptops and phones today, they generate their addresses using privacy-enhancing techniques, and prior work has shown that the host part changes frequently on the order of hours. Now, if these devices are using privacy-enhancing addresses, that means there are no privacy issues, right? Well, not exactly. Because even if the host part changes frequently, that only prevents fingerprinting an individual device. If the network part remains the same, it is still possible to track a subscriber over time. We therefore focus in this work upon the dynamics of the 64-bit network part. Now, in this particular example, I had shown the home router receiving a /64 from the ISP's DHCP server pool. However, the considerable flexibility in IPv6 addressing means this need not always be the case. Subscribers can be delegated prefixes that are shorter than a /64 also. In this example here, the subscriber has been allocated an entire /56 prefix, and the home router has chosen the first available /64 within this /56. Now, why does this matter? It means that the subscriber now has the ability to potentially cycle through various prefixes in the delegated prefix, affecting applications like host reputation. If we wish to block a malicious device in a subscriber's network, even blocking its /64 prefix may not be sufficient, because the subscriber may be able to use a different /64 within the delegated /56. While we are primarily interested in V6 dynamics, most residential networks today that offer V6 also offer IPv4 connectivity. Thus, we additionally investigate IPv4 assignment patterns in these dual stack networks and contrast our findings against IPv6. We analyze address assignment practices in dual stack networks using two complementary datasets along two axes. In our analysis of temporal dynamics, we study how long IPv4 addresses and IPv6/64 prefixes can identify residential subscribers. In our analysis of spatial dynamics, we study which IPv6 prefixes can identify residential subscribers. Do subscribers receive a /64 delegated prefix, a /56, a /48, etc.? We also investigate where addresses move upon reassignment, whether subsequent addresses assigned to the same subscriber are close together in the address space or far apart. I'll next describe the two datasets that we use for these analyses. The first dataset consists of measurements from the RIPE Atlas platform, which consists of around 10,000 active probes. Probes are mostly hardware devices in volunteers' networks, many of which are in large residential networks such as Comcast, Deutsche Telekom, etc. Probes conduct a variety of measurements. We use the IP echo dataset, which allows us to study the IPv4 address and IPv6/64 prefix of residential subscribers over time. In each IP echo measurement, the probe sends a packet to an echo server that allows identifying the public IPv4 and IPv6 address of the Atlas probe. These measurements are conducted every hour, thus we can see the v4 and v6 addresses over time. This allows us to detect when an assignment change occurs and allows us to measure the durations of assignments. Our other dataset comes from a large CDN. Dual stack clients will sometimes connect to one CDN server over IPv4 and another CDN server over IPv6 during the same transaction, resulting in an association between the IPv4 and IPv6 address. The CDN aggregates the IPv4 address seen in the association to a /24 and the IPv6 address to a /64. Over time, as the client contacts the CDN, we obtain more associations of a v4/24 with a v6/64, allowing us to estimate the duration of individual associations. These durations give a lower bound on the assignment durations of IPv6/64s. Although this lower bound duration is less precise than the durations we get from RIPE Atlas, the enormous footprint of the CDN gives wide coverage. So let's dig into what we learned about temporal dynamics. Now, let's look at how to analyze the assignment durations we obtained from our datasets. Suppose that we observed the following three assignment durations. Assignments lasted for 24 hours, 24 hours, and 12 hours respectively. We want to analyze a distribution of these assignment durations, so let's plot a CDF. The x-axis here will show the address duration in hours. The y-axis shows the CDF. Since there are three samples and two of them are 24 and one of them is 12, at x is equal to 12, y is going to be equal to 1 by 3, so 0.33. And at x is equal to 24, y is going to be 1. However, we go for an alternate representation. In this alternate representation, we weight each duration by the duration itself and plot the distribution. Let me elaborate with this example. Let's sum up all the durations. That gives us a total of 60 hours. Next, we try to find what proportion of 60 hours each individual duration comprised. Again, in the graph, the x-axis shows different address durations, but the y-axis now shows the fraction of total address duration. For example, 12 hours comprised 20% of the total duration of 60 hours, because 12 by 60 is 1 by 5 is equal to 20%. and 24 hours comprised 80% of the total address duration. Now, why do we go for this representation? Suppose we add 100 new durations, each 1 minute long, and replot the CDF and weighted CDFs. As you can see, the two graphs look quite different, with the unweighted one on the left-hand side and the weighted one on the right-hand side. The weighted graph answers the question, at any point in the first 3 days of January, what is the probability that we observed an address lasting X hours? This is ultimately the question we are trying to answer. If we had to blacklist an IP address from an ISP, how long should it remain on the blacklist? When we consider durations for an entire ISP, we aggregate all durations seen from all probes for that ISP. So let's take a look at what the weighted graph looks like for 6 large residential ISPs with many RIPE Atlas probes. We found that IPv6 assignments to residential subscribers typically have much longer durations than IPv4 assignments. The graphs here are derived from RIPE Atlas data and show IPv4 address durations on the left and IPv6/64 durations on the right for large ISPs from around the world, including Deutsche Telekom, Comcast, British Telecom, etc. Each of these graphs is showing a weighted CDF of durations. Now, we discover a few modes in these graphs for v4, indicating that some of these ISPs renumber addresses periodically. In v4, we observe 24-hour durations are common for Deutsche Telekom. 1-week durations are common for Orange. 2-week durations are common in BT, etc. But in IPv6, we only see evidence of periodic renumbering for Deutsche Telekom among these ISPs. And more generally, we find that the v6 curves for these ISPs are shifted to the right for most ISPs, indicating longer IPv6 assignment durations. We were also able to corroborate our observations of long IPv6 assignment durations on a broad scale using the CDN dataset. We cover these analyses in greater detail in our paper. These long assignment durations suggest that IPv6 addresses can be used as long-term subscriber identifiers. While this is good news for IP address-based applications like host reputation and geolocation, it raises privacy concerns, since residential subscribers' IPv6 prefixes can be used to identify them for months and sometimes even years. We next investigate spatial dynamics of IPv6 address assignment. In this talk, I'll focus upon the first question and describe our analysis of which IPv6 prefixes can identify residential subscribers. I encourage you to read the paper to find our analysis on where addresses move upon reassignment. Recall that IPv6 subscribers can be delegated prefixes of variable lengths. While the RFC specified that at least a /64 should be delegated, it's up to ISPs to decide the exact prefix. RIPE Atlas probes allow us to see the /64 prefix that is being announced in the home. We use a heuristic that many home routers choose the first available /64 within their delegated prefix to advertise to the rest of the home, resulting in the last few bits of the /64 prefix being 0. In this particular example, the delegated prefix is 2601:47:4500:5C00. The first /64 is the one where the last two digits in the quad, so in 5C00, are both 0. So for a given subscriber, our approach is to look at all different IPv6 /64s, that is, the network parts of v6 addresses over time, and identify how many bits from the right are always 0. The slide shows /64s observed by a sample probe in Sky UK. We see that the rightmost 8 bits of the network prefix are always set to 0. So all of the quad digits just before the colon are always 0, the last 2 of them, and these comprise 8 bits. So subtracting 8 from 64, we therefore infer that this subscriber is being delegated a /56 prefix. We use this heuristic to investigate the percentage of subscribers with various lengths of inferred delegated prefixes across different ASs. The graph on the left shows the percentage of Atlas probes with various lengths of delegated prefixes in Sky UK. We see that more than 75% of subscribers appear to have been delegated /56s. However, this behavior varies across ISPs. In Free, most subscribers appear to be delegated /60s, and in NetCologne, many subscribers appear to be delegated /48 prefixes. This means that a /48 prefix can be used to identify an individual subscriber in NetCologne. From a host reputation perspective, this means that a subscriber in NetCologne has the ability to cycle through 2 to the 16 /64s to evade rate limits at the /64 granularity. So in order to effectively rate limit a subscriber in NetCologne, a full /48 prefix has to be rate limited. However, blocking a /48 in free may be counterproductive since it may block other subscribers. We were able to validate these results across several ISPs, including NetCologne and Sky, and were able to corroborate our results using the CDN dataset. Again, for these results, I encourage you to read the paper. These results highlight that when it comes to IPv6 prefix lengths, there is really no one-size-fits-all approach. Different ISPs use vastly different ways of assigning IPv6 addresses, and our technique can help towards determining these prefix lengths, boding well for host reputation and geolocation, but also hinting at looming privacy issues. So in this work, we empirically analyzed address assignment dynamics using 2 complementary datasets. Our analysis of temporal dynamics revealed that IPv6 /64 assignments to residential subscribers may remain unchanged for months and sometimes even years. Our analysis of spatial dynamics show that IPv6 prefix lengths delegated to subscribers can vary considerably across ISPs. In the paper, we also show that subsequent addresses assigned to the same subscriber are often from the same /40. These observations affect many applications and also raise privacy concerns, such as whether IPv6 addresses and prefixes of various lengths should be considered PII. And with that, I conclude my talk. Thank you very much for your time.